time for the final segment of the Machine Learning Master class. Hope you've had a good time and that you're learning a lot. So thank you, Jalen, for the idea. I just want to provide a brief introduction to deep learning via Keras. So Keras uses TensorFlow. It is, I would think it's kind of the most commonly used, I guess, library out there for deep learning these days. It's high level compared to TensorFlow, which means it's a little easier to use. And at the beginning, this is stuff that you've already had. This is just loading a data frame, the California housing data frame. Be nice to see that updated. Splitting the data, you've seen that. Okay, and then hey, here's a linear regression. No, this is not a percentage. This is the mean squared error. Actually, the RMSE. Okay, so we've done all that before, but now let me quickly show you just how deep learning works. You can use this code to build any deep learning regressor, more or less. So you import usually two things separately. The sequential model, that means, it goes in sequence, and dense, which means all nodes are densely connected. So I would say, I guess overall the difference between deep learning and machine learning is that in machine learning, you're going straight from the model, like the X to the Y, meaning like in regression, you're just multiplying them out. But in deep learning, you have what's called hidden layers. And so from the hidden layers, there's just a lot more opportunity for mathematical intricacy. And you're really trying to pick up upon small gains going from one hidden layer to the next. Okay, so you're supposed to really specify the number of columns, which this is how you start it, right? How many mathematical operations do I start with? Well, you start with 8. That's why I have the shape up here, because this is 8 columns. Then you initialize the model, which is called sequential, just like you always would. I guess I need to run this X shape. And then you can add a hidden layer. I just chose also 8. This could be any number. You could like double it to 16. You could pick anything. Okay. And so again, the idea of the hidden layer is that there's not just one multiplier here. There's going to be another one. And what's cool about it too is it's actually going to, right, like it's going to take each column and find a unique, say, multiplier to go to each of the next 16 hidden layers. Okay. And so you can see it's specified here that the input shape is the number of columns. And you also do need an activation. And this allows for nonlinear dynamics. ReLU, it's like rectified linear. It's like a straight line and then it goes up. So it's basically like y equals x, except when it's negative, it's 0. And then finally, by the way, you can do as many of these as you want. So just to show you, you could add another of these. You have many hidden layers as you want. So this one is 16 nodes. Maybe then add a hidden layer with 8 nodes here. Okay. And now the input shape would not be the number of columns. I think you don't actually need to specify it beyond the first one. I think you can keep the same activation. But importantly, you need an output layer of 1 because it's one prediction, right? This is in effect like one row, right? It's got all these different columns. Okay. So this is just like really the model. You haven't done anything yet. Again, what's kind of cool about these deep learning, you get to pick like how many hidden layers do you want? I have 2. You could have 10. You could have 1. You could have 100. Do note, the more you have, the longer it's going to take to build. And also what's cool is you get to pick the number of nodes. If you go too crazy, like I'm going to do 100 hidden layers with 1,000 nodes, it's going to be too much. It's going to take too long to build. So I would start small and then experiment. Okay, you've also got to compile it. See, Keras is different than sklearn, okay? I don't expect you to like memorize these details or keep them all. I just want to give you little indicators in case you want to come back to this at another time. Optimizers, how do you account for the adjustment through the deep learning each time? It uses back propagation. You get like a prediction, then you got to go back and make new changes based on the prediction. And the optimizers kind of different strategies for doing that. The loss is mean squared error standard. And finally, you fit it to the training data. You can pick the number of epochs. I'll shorten this to 10 so it doesn't take too long to run. That means how many rounds does it get to go through to improve? Maybe 15. Maybe 20. Let's take the middle. And then we evaluate on the test set, which we already have. And we're getting the root mean squared error at the end. Okay, so let's just try it. I know it's a lot of code. So it's taking a moment to get going. What's nice about this is it'll show you the code as it's building. So it's showing you the loss. Now it's kind of interesting. Oh my gosh, it's not improving at all. Usually you will see improvements from one round to the next. And this could simply be because like it just, I don't know, I guess it couldn't do better than it did the first time. Totally rare here. There are possibilities there's some error that shouldn't be there. But we'll let it go ahead and run out and see what we end up with at the end. What's the RMSE? It's going to print it on the test set. So this is basically like the training. And deep learning is its own kind of big branch of machine learning. 2.4. Okay, so not ideal initially. Let's just see if it might be hard to change. Let's cut these down. If I just do 10 epochs, and again, maybe I just do want the one layer. You can like easily just trying to at least comment it out. And this is from previous notebooks. I'm going to assume it's fine. Just run it one more time and see if do we get a change in the score. Yeah, you can see it's adjusting, and it's it looks like so for whatever reason it can't get better than that 5.5560. Oh, slightly there. And you could totally set these things up to stop like as similar score to stop like when they don't show improvement over time. And this is, I guess, showing the multiple epochs. And then is there anything else in this notebook? That is all. But I will say this. I've spent time before slightly better score here, like training over more epochs. Although that was actually an old version. I'll just let it run. So again, just giving you a little introduction, things to think about for the future. So when it comes to machine learning, you should know that the techniques that we focused on in this class, primarily XGBoost and tree-based models, are ideal for tabular data where you have rows and columns of, say, structured numbers. But deep learning has a huge edge when it comes to unstructured data like images and text. So if you're doing machine learning with those topics, I would encourage you to focus in on deep learning and, keep going forward. Wish everyone well in their journey. I think it's noble and challenging to step forward, as everyone who's watching this video has, to make the commitment and effort to get better at machine learning. It's a long journey. There's a lot of great material out there. So keep up the fabulous work. Let us just end with the code. Like, how is it doing? Oh, this is a long one. It's got 100. You can always run it and play around with it. And last thing on this notebook, by the way, is I did take the time before to try to make it as little like code as possible. That in effect is deep learning. So keep up the great work. Is it doing any better? Yeah. Let it run.